Thank you for the introduction. So the university is Universidad de Juan Carlos. It's just easier to say URJC. So from Madrid, so I'm Gabriel, Cirio, and I'll be presenting our work on how to simulate efficiently fabric at the yarn level. So the idea behind our work is to simulate entire garments at the yarn level, not just small pieces of fabric. So our group is above all a computer graphics group. So one of our main application areas is computer animation, visual effects, the movie industry. However, we also wanted to develop a model that could be used in other areas beyond computer graphics, where realistic cloth models are actually required. So like fashion industry and hopefully some textile engineering field. So we're really aiming for realism here. So the reason why we want to model cloth at the yarn level instead of relying on triangle meshes, which is often the case for full garments, is that we want our model to be realistic at the macroscopic level, but also to capture mesoscopic effects. So there's obviously plasticity effects such as fracture, tearing, snags, bold, frayed edges, the images you're seeing above there. There's also more complex effects such as the curling of cloth of some knits around the edges, or hysteresis effects due to internal friction of the cloth, which usually leads to some nice persistent wrinkles across a garment. These are hard to capture if you're not dealing with yarn level models. So of course there's several approaches to simulate fabrics using yarns. Some final element models for high degrees of accuracy, multi-scale approaches to focus on the computational power only what's actually required. So the work closest to ours is that actually also comes from the computer graphics field, and with some presentation earlier by or the recording at least. So this body of work from here, Cornell, very nice, very impressive, very realistic. They can simulate the behavior of knitted cloth quite well. However, the main problem with all these approaches is that yarn contact is actually computed explicitly. So every yarn is modeled independently, and you have to run for every yarn a collision detection routine. You have to detect the collision against the other yarns, and then you have to resolve that contact. So apply some force or some impulse or something like that. So that's very computationally expensive, of course, especially we're dealing here with like millions of degrees of freedom. And it also imposes a restriction on time step because you don't want to miss any collision. If you miss one collision, you might have your whole cloth unraveling. So in order to deal with this robustness problem, you need to be careful with your time step. So I'll be talking about how we actually discretize the fabric to address these issues while capturing the most important degrees of freedom, and how we design the forces that govern the behavior of cloth. So first, discretization. So in knitted cloth, yarns are laid out in a chain of loops along a row, as most of you probably know. So these loops are usually pulled either up and down to the loops of the previous row, creating a stitch, a neat furrow stitch, nothing new here. So these stitches, yarn rub around each other, and this contact is friction that actually holds the fabric together and plays a fundamental role at the macroscopic degree. So the key idea here is to assume that these contacts are persistent. These contacts always exist throughout the simulation. They're always touching, they will remain in contact. So we actually get rid of this assumption, very strong assumption, but we get rid of collision detection and resolution altogether. So that bottleneck is gone. So we'll see how this plays out, what it actually means. So how do we actually discretize the fabric then? So if we zoom at this single stitch, we can see that their yarns are wrapped around each other at two different places. So we're creating two contact regions, and we discretize these contact regions using contact segments. So one for each region. And this is, I guess, some similar concepts with talk that we saw this morning, the first talk, with the reduced model. So now instead of having this complex contact configuration, we just have a segment, 1D structure. And the segments are shared by both yarns, and at each contact segment, we place a node at the end of each segment, and then we call that a contact node. And that's where the degrees of freedom of the fabric actually are. So then the rest of the utilization just follows by laying yarn segments between the contact nodes. And we get this pretty simple discretization at the bottom. It's like honeycomb shape. So instead of having this complex volumetric shapes, we have this flat 2D honeycomb simple representation. As we will see, this discretization captures most of the important degree of freedom of our pattern. So the same discretization can be applied to woven cloth. In woven cloth and woven cloth, yarns are interlaced, so we put a contact node where warp and weft yarns are actually in contact. And this time it's even simpler because we don't have a contact segment, it's just contact node. So it could also be used in woven cloth. And the examples I will show will have woven cloth and knitted cloth. So the other key insight is the degrees of freedom. So contact nodes have these three special degrees of freedom. They'll call X here, vector X, or X, Y, Z coordinates in space. The node can move around, can stretch and bend the yarns, and we call these the Lagrangian degrees of freedom. But we also have sliding degrees of freedom that we call U and V, and these allow the yarns to slide along each other. So these we call the Eulerian degrees of freedom, and then these are the ones that can actually accommodate the plasticity effect within the cloth. So yarn can slide within the cloth structure. So this discretization is enough to capture all the interesting deformation modes in the fabric. As we'll see later, it's much more compact representation, so reduced model. And it avoids running collision detection and resolution altogether. So in the end, we have generalized coordinates. Each contact node has 5 degrees of freedom, 3 special coordinates, 2 sliding coordinates. This is based on the great work of Sweat and collaborators in 2011 on constrained rods. And since we have generalized coordinates, we use the Lagrange equation, which is a reformulation of Newton's second law, basically, well suited for generalized coordinates. I won't go into the details about this. So now that we have discretization, I'll show you how to derive a set of forces based on these 5 degrees of freedom nodes that will govern the behavior of the cloth, and I'll show you some examples. So all our segments are simulated as elastic rods. Pretty standard model for this type of geometry and material. So here I'll be showing just the energy formulations at the bottom, so you can see that it's pretty simple formulations in the end. So we have stretch, we measure the elongation, you have an energy which is quadratic on the elongation. We have bending in 2 consecutive segments, the energy is quadratic on the angle between those segments. We have, for the case of woven cloth, we can simulate shear. So shear is this rotation of yarns around contact nodes. The energy is again quadratic on the angle between 2 contacting yarns. And then we have this yarn friction. So, like I said, we have this sliding coordinates where yarns can slide along each other. But if we don't do something about it, it will actually slide and the cloth will unravel. So it's friction that actually holds together these yarns. And here we leverage our sliding coordinates formulation, and we add a zero-length spring right, at each contact node. And this is what holds the yarns together, otherwise it keeps them from sliding. So this is static friction, it holds the sliding coordinates in place. But we can also have dynamic friction, where the anchor points of the spring just follows the sliding coordinates while generating maximum friction. Very simple formulation. It's a benefit of our sliding coordinates. We use Coulomb friction here, so the force, the friction force depends on the normal force at the contact point. And for this, we just offset both yarns along the contact normal to account for trim. And then we compute stretch and bending and predict it on the normal to get the compression force. So with this, we're going to have some results. So this is a shirt, a woven shirt. It's 2,000 yarns, 350,000 contact nodes. That's more than 1 million degrees of freedom. So you can see the high resolution of the fabric. Of course, you don't see the yarns. There's so many, and we're a little bit far away. So high resolution, you can see all the details. It's robust even with the sudden motions of the character. Another example, this is a sweater. So this is knitted. Just so 56,000 loops, 250,000 contact nodes. Real quick, we compute everything on the GPU, the graphics processing unit. So this is roughly 2 minutes of computation time per visual frame that you're seeing. I won't go into details about the implementation, but of course I can ask any question about it. So once the contact nodes slide, the yarn slide, we need to deal with the contact between adjacent loops, so the yarns don't overlap each other. So again, the benefit of our sliding coordinates, we just need to penalize proximity of these two sliding coordinates. And with that, we can simulate other phenomena, such as snags. So pulling one yarn out of the cloth. So something we're sadly all been exposed to, and as you can see, so because you pull the yarn and then the fabric comes with it, forming a distinct pattern of a snag. So a plastic effect, only possible or easily possible thanks to the yarn level formulation. This is another little more artificial snag with pulling two yarns at the same time, and it's most Cirio that have a good close-up of the yarn structure. So this is a woven example, but it can be perfectly done in a knitted example as well. Some other results. So we can also model curling. The curling of the stockinette pattern in knitting exhibit a curling behavior at the edges due to the wrapping of the yarns around each other. So our model can capture that with a specific force that we designed, and as you can see, you see the curling naturally. This is half speed, so you can see the whole behavior. We can also model shear friction. So when woven cloths undergoes shear, this and hysteresis effect into shear friction. So we added a very simple friction force, similar to the, yes? Oh, you had a question. We had a simple friction force similar to the sliding friction force that I showed before. And with that, we can get persistent wrinkles across the fabric very naturally because shear friction changes the rest configuration of the fabric. So as you can see, you have on the left no shear friction, on the right you have the shear friction, and then when you go back to the rest position, now there's a persistent wrinkle because the rest configuration actually changes due to shear friction. And it's very easy to model here. Other examples, tearing. So naturally now we can just cut the yarns when we fill the cloth. You have all the nice effects of loose yarns, frayed edges, anything that comes for free with the model basically because we're doing yarn level instead of just using a bunch of triangles. This is woven cloth. Now another example of knitted cloth. You can see the loops unraveling as we pull. Also patterns. So in knit cloth, different patterns can be obtained by varying knitting frill stitches, and this pattern leads to dramatically different macroscopic behaviors. So you can see the results here for these different patterns. So some fancy patterns at the top, some very more simple patterns at the bottom, and a woven example for comparison. So especially the rib pattern is interesting. Bottom row in the middle. So each pair of stitches goes in opposite direction, and it leads to a natural compression of the fabric in these nice rib structures. So in all these examples, we use the exact same yarn properties, same sizes, we only change the pattern, and we get this different, dramatically different draping behaviors for each sample. One other cool thing that you can do with yarn level, not only our model, but with yarn level models, is the natural emergence of macroscopic non-linearities. So this is a rib sample that is naturally compressed due to curling. And then if I want to stretch this sample, I'm first going to fight against these curling forces. So there's this compression. Once I've unraveled that, I'm going to be fighting against the bending force of the loop deformation. And then in the end, I'm going to be fighting against the actual yarn elongation, which is almost inextensible in most cases. So here's the actual graph. This is not handmade, it's actually we measure the forces on this simulation example. Play it in. You can see the very high non-linearity, which is also easy to have here with yarn level modeling, but hard to do if you were just using a triangular discretization. So to conclude, I'm just presenting our work on fabric at the yarn level. So it's a discretization used persistent contact nodes. Contacts are persistent, except when you actually do fracture, so you split the nodes. We use sliding coordinates, simple force models, and we achieve some nice ground level and microscopic effects. So, of course, limitations and avenues for future work. First of all, parameter estimation. Right now, we use just arbitrary parameters. I would say they don't match anything in the literature. So we want to do some measurements, more like data-driven way of setting the parameters. And also, the major drawback right now is probably memory consumption. We run everything on the GPU, so it can actually be tractable, be fast. And it eats a lot of memory, of course, and we usually go over the memory of the GPU. So we're looking to ways of not having to solve this huge system and use some other approaches for the solving part. That concludes my presentation. Thank you very much.
Two short questions. How do you deal with bending of the yarns? You mentioned the actual features information, and which system you use for the GPU? CUDA or?
Right. Okay, so for the bending, we just measure the angle between two consecutive segments. Okay. And then it's just an energy which is quadratic on that angle. So very, very simple, very classic in computer graphics at least. For the implementation, we do use CUDA. Yeah.
Yeah, so I think maybe you said this, so you're simulating on what we'll call your reduced order model, your stick model, but and then somehow you're able to then overlay, spline geometry on top of that.
Right. So it's the discretization. You can say it's like a flat discretization. Then we know the normal of the contact. We compute at least the normal of the contact, so we know into which direction we have to. We move the yarns when we want to have the actual volumetric representation, and then we use splines to just recover the curves. So it has its limitations. We don't enforce, since we use splines just like that, we end up having too much material in a place where it should be a shorter length. So that's definitely something we need to improve. But right now that's the approach we take. And we also do that for to know the normal force, the compression force, the friction. We also need to separate the yarns. So now we have crimp, and then we now have bend, more pronounced bending, and some more intricate mechanics at that contact point.
Any other question? Yes.
Just a quick one concerning the simulations, which were very beautiful. When you showed the figure that was turning and everything, I think there's also shading involved. Are there other layers you didn't talk about that are necessary in order to get this realistic movie?
Okay, so the question is about the rendering of
right.
the visual rendering.
Yeah.
So I actually have a whole paper about it, which from one of the authors of this paper, and it's a volumetric rendering approach. So it includes shading. I'm not the expert on that field, but it's definitely.
So that comes on top of the.
Yes. Exactly. This is a body of 3-4 papers that I just summarized there.
Okay. Thank you.
Let's thank our speaker one more time.